Alright, friends and neighbors, time now for a little networking with TCP. And we're not going to do the whole TCP protocol at this point. That would be a lot, but I thought we could talk about sequence and acknowledgement numbers. So as we know, Transmission Control Protocol RFC 793 is really about reliable end-to-end connections. And so what that means really is that it's about keeping track of all the bytes that have been flowing back and forth and also not overrunning your partner in your communication. So the two sides are trying to communicate in a nice, calm, well-mannered method. We also want to have some way to recover lost data. So that's really what we mean when we say it's reliable end-to-end connection oriented. And in this particular video, we're going to talk about how we manage to keep track of all of the bytes that are involved in the conversation. So what we really want to focus in on are the sets of numbers that we call the sequence and acknowledgement numbers. Now the sequence numbers and the acknowledgement numbers both have a couple of flavors. So we have the raw numbers, which are randomly generated values that we can find in the hexadecimal. And the base 10 values are shown here. So for the sequence number, it begins with 142, and for the acknowledgement numbers, it begins with 325. And I guess at this point, I will mention, and I'll regularly remind you over the course of this particular video, that the sequence numbers are what I have to send, and the acknowledgement numbers are what I believe you sent me. And so there's actually two sets of sequence numbers, one for my side and one for your side. Or we might say one for the client side and the server side, and then the acknowledgement numbers are what a particular endpoint believes the other side sent and what they expect next. The raw sequence and acknowledgement numbers are those actual random number values, and there's the hexadecimal representation and the base 10 as we see here. Now the relative sequence numbers is just Wireshark being very helpful. And that is saying, listen, we could try to keep track of these crazy random numbers because sequence numbers come from a fairly large field, lots of values. But it would be easier if we just said, well, that random number is the beginning, and so I'm going to start at that point counting at 0. And so that becomes a relative number. So it's a lot easier to understand what's going on as we go through there. So I will try to keep track of both the relative and actual or raw sequence and acknowledgement numbers as we go through the examples here. And this is just the RFC view of the header, and remember that we are focused on just these two particular fields right here. So the sequence and acknowledgement numbers are what we use to keep track of all of the bytes that have been sent between the two sides. So at the beginning of the conversation, what happens is each side picks their sequence number, and the opposite end acknowledges those sequence numbers. So there's two sets of numbers that we have to be aware of. Now the sequence number is actually pretty straightforward. All that this is the set of bytes that one side has sent. So for example, if I'm sending data to you, I will pick a sequence number and I will send the data, and my sequence numbers begin at that random number, and then I just increment based on the amount of data that I've sent. That's it. And we'll see exactly how that works here in a second. The acknowledgement numbers are what I believe you sent me. So in this conversation, you will have had to tell me what your sequence numbers are. And the minute I get data from you based on your sequence numbers, when I acknowledge those, I'm going to say, I got this set of bytes from you, and the next thing that I expect is the last sequence number from you plus 1. So it's a little confusing, but that's how we keep track of it. And so we'll do an example, and hopefully it'll be more clear. Now to begin with, we know that TCP connections start with a three-way handshake, the SYN, SYN-ACK, ACK, and hopefully you've got a pretty good handle on that. But the important thing that we want to remember is not just that we did this nice exchange of flags, but what's the purpose of the connection handshake? So the handshake is that set of packets, but inside that set of packets, what we're really doing is we're setting up the conditions for the connection. most notably the sequence numbers that both sides are going to use, and the window size that each side is going to use. So each side picks their own sequence number, and each side picks a window size. Now we're going to talk about window size in another video. So each side has a sequence number. So side A says, this is my sequence number, and here's my window size. And side B says, here's my sequence number to begin with, and here's my window size. The two sequence numbers have nothing to do with each other. But when side A sends more data, it says, these are the sequence numbers that I just sent, and here's what I got from you. So these acknowledgement numbers are based on side B's sequence numbers. And then side B sends some data. Here's my sequence numbers. And then it says, by the way, I got this data from you, and so these acknowledgement numbers going back the other way are based on the sequence number from the other side again. Piggybacking simply refers to the way that we acknowledge something. If a packet has a set of data going across, meaning that there's sequence numbers going across, and in that same packet there's acknowledgement numbers from what the other side sent, that's piggybacking. We're doing two things at the same time. If we're just acknowledging without sending data, then that's not piggybacking. Now this is just a quick example showing you the handshake capture, right? We've got the SYN flag right here, we've got the SYN ACK here, and then the ACK over here. But also we've got the sequence number, and this is a relative sequence number set to 0. Notice that there is no acknowledgement number here because no data has been sent. Sequence number for the other side. Now they both say 0, but those are relative. So the numbers that are actually used, the raw values, are not 0, of course. And here's the acknowledgement number, which is just one more than the original sequence number. And then, of course, the sequence number, the next chunk of data, and then the acknowledgement number here is one more than the sequence number from the opposite side. So this is an example of a handshake, and then we see the advancement of the sequence numbers and the acknowledgement numbers through the handshake. And just for fun, I'll note that we got a window size from one side and a window size from the other. Terminating the connection is another handshake that goes on. I'm not going to spend a lot of time on it, but essentially the flags that we're after right there are the fins and ACKs from both sides, right? Both sides have to acknowledge the termination of the connection, and when we do that, we're also trying to clear out all the buffers, make sure that all the data gets sent. And this is just an example of the termination phase, the flags that we use, right? One side is the terminator and sends the fin flag, and the other side has to acknowledge that, but then that side also has to decide to close the connection, and then that's acknowledged by the opposite end. So again, the sequence numbers. It is a random number that is set at the beginning of the conversation. And we have two sequence numbers to pay attention to. Each side has their own sequence numbers, and they have nothing to do with each other. Now, the acknowledgement numbers are for your recognition of the other end. So, again, sequence numbers going this way, sequence numbers going this way. Acknowledgement numbers going this way are about the sequence numbers from the other side. Acknowledgement numbers going this way are about the sequence numbers on this side. So, the acknowledgement numbers are what we use to recognize that you got a certain set of sequence numbers or certain bytes from the other side. So here's an example conversation that people might actually use if they were trying to do things like TCP does. So person number 1 says, how is it going? And person number 2 says, just fine, how about you? But the TCP part is person number 2 says, by the way, you just said, how is it going? And so that is the acknowledgement of the data or the sequence numbers that were sent. And then person number 2 also says, by the way, I expect you to say, good, seen any good movies. And so that's an expectation of the next set of data. So person number 1 says, good, seen any good movies? By the way, you said, just fine, how about you? And I expect you to say, no. All right. Now, it's not really about predicting the conversation. We're not trying to figure out the actual data that's going to be sent, but rather keeping track of the data that is sent. So probably a more accurate way to think about it would be, how is it going? by the way, that was 16 bytes from my beginning sequence number. And then the person number 2 would say, just fine, how about you? By the way, this is 24 bytes from my beginning sequence number. And you gave me 16 bytes, so the next thing that I expect from you is byte number 17. Oh, good. Seen any good movies? So that starts at byte 17, and this has a length of 26. By the way, you gave me 24 bytes, and I expect number 25 from you. So that's actually how it might go. And you can see how clunky this is, but you would never have any confusion in a conversation if you actually try to do it this way. Okay, so let's look at an actual TCP conversation with Wireshark and with a slide that tracks all of the sequence and acknowledgement numbers. So this is the conversation and the packet numbers that I'm going to use, but let's actually take a look at the trace as well. So here's our friend Wireshark, and I hope that you can see this on your screens okay. And so I have a conversation between 192.168.1.1 and 192.168.1.254. And in this particular conversation, 1.1 represents the client and 1.254 represents the server. And so we can see at the beginning we've got this back and forth. This is simply the SYN, SYN-ACK, ACK of the initial handshake. But if we click on this, we can see that, and I'll bring these together a little bit, we can see that the relative sequence number is 0. The actual raw sequence number in base 10 is 314.629.536. Well, what's the hexadecimal representation of that? We can see down here that it's a 4-byte field. That's why there's a lot of sequence numbers. So it's 12C0DDA0. That is our beginning hexadecimal representation of the sequence number for the client. I would not want to try to keep track of this, so it's a lot easier to go with the relative sequence numbers. All right, so what's the acknowledgement number? Well, there is no real acknowledgement number because the other side hasn't sent us any data. We have no idea what the sequence numbers are from the server, and so they're just set to zeros here. Okay? So in this case, they all are the same value. Now, the server comes back and says, well, here's my sequence number, beginning point. And of course, we can see down here below, it's 9053C2FD. Again, nothing to do with the sequence numbers from the client. The server is just saying, this is where I am starting. And here's the base 10 number, base 10 representation of that. Here's the acknowledgement number, though. So the acknowledgement number is one more than the sequence number sent from the client, meaning that I got what you sent me and I've processed it. And so the next thing that I expect from you is one more than the last thing that I processed. And if we take a look down here, we can see it's 12C0DDA1, which is one more than the sequence number here. Okay? Now the client comes back and says, all right, here's the next chunk of data that I have to send. And that's the raw value. And we see, yep, the server expected this number, and that is in fact what I'm going to send. By the way, I'm going to acknowledge what you sent me, which is essentially just your beginning sequence number. So I've just incremented that by 1. If you think back here, the sequence number from the server ended in FD, and now we end in FE, which is one more. Okay. Now these are just really setting the initial sequence numbers, right? We haven't actually sent a lot of data. We've sent really 1 byte maybe back and forth. Now the next thing that the client does is says, can you send me a web page? So this is an HTTP GET inside a TCP packet. So I'll show you that real quick, right? So there's an HTTP GET, but really what we care about obviously is the what's going on with TCP. All right, so the sequence number here is 1 because this is actual data, and this is the beginning. But we also know how much data is being sent. So the headers here will also give us a length and the amount of data. Okay, and so again the raw sequence number, And then the acknowledgement number here hasn't changed because we haven't gotten anything from the other side. Now take a look. Wireshark is telling us it's 406. Okay. Well, this is just the amount of data that this is carrying. So Wireshark is just being helpful again here and saying, looks like this packet's got a lot of data. We are sending 405 bytes worth of data. And the server comes back and says, well, I'm going to send my sequence number. We can see that it's based on these values, right? The server's sequence number. But look at this acknowledgement. This acknowledgement is 406, meaning that I'm acknowledging the 405 bytes that you sent me, and the next thing that I expect is byte number 406. So we're keeping track of the size of this packet, and we're acknowledging that we got the previous 405 bytes and we're able to process it. Now what's interesting here is that was packet number 6. Packet number 7 is also from the server. So at this point we should not expect an increment in the acknowledgement numbers. What we see here is an increment in the sequence numbers, right? We went from 1 to 561 because we were in fact sending part of a web page down. But the acknowledgement number is still 406 because we haven't gotten anything from the client. So we send, Wireshark is telling us that the next sequence number is going to be 561 because we're actually sending 560 bytes worth of data. And if we looked in the IP header, we would see that it's set at 600. Well, why is it 600? Well, it's 600 minus 20 for the IP header minus the size of the TCP header, which is normally 20, plus any additional data that might be in there like options. But in this case, it's 560, right? Whoops, let me go to, close this. It's 560, so we just have a 20 byte TCP header as well. And then we're back on the client, and the client says, here's my next sequence number. And by the way, I'm going to acknowledge 1121. Well, how does that work? Well, we're acknowledging 2 sets of data sent from the server. So the server sent us 560 bytes and then another 560 bytes here. The next sequence number would be whatever the 2 chunks of data were added together because we sent 2 packets. Now in this case they happen to be 560 and 560, but there you have it. So that's why we're acknowledging 1121 here, and the 1121 is 1 more than the 2 chunks of previous data. Alright, so let's do the slide version of this. We can see this first part is the handshake with the SYN, ACK, ACK, and then we can see the details with regard to some of the sequence numbers and acknowledgement numbers in the windows over here. Now, I've put it down here in this table that we've got this original sequence number, relative is 0, and then we've got the hexadecimal. 0 is the ACK number, so I didn't bother to put that there. And when the server comes back with its part of the handshake, it sets its sequence number and then provides an acknowledgement number of the next expected thing from the server. And of course, the server responds with the next expected sequence number and acknowledges the server and then says, by the way, the next thing I expect from you is this chunk of data right here. And then we saw the HTTP GET, so a big chunk of data from the client, right? It just says, here's my formatted HTTP GET request. Turns out it took 405 bytes to do that. And the acknowledgement number did not change because this was again from the client, right? 1.1 and 1.1 sending to 1.254, 2 packets in a row. Well, the server comes back and says, well, here is my sequence number. Here comes the web page. And here's the thing that I'm acknowledging from you. Again, based on the client's sequence numbers. So you sent me 405 bytes. The next thing I expect from you is byte 406. Now the server comes with 2 chunks of data, right? 1.254 and 1.254. Comes down, and so there's 2 chunks of data. So the acknowledgement number, or the the sequence number starts at 1, because this is the first chunk of data, and then the next sequence number starts at 561, because there were 2 chunks of data, both 560 in size in this case. The acknowledgement number doesn't change because that is what is expected from the client, and the client is not transmitting at this point, and so on and so forth. So hopefully looking at the Wireshark captures and then also taking a look at this sort of table version of that helps you get through how the sequence and acknowledgement numbers work and how they keep track of the data from both sides. Alright, so this was a discussion of TCP sequence and acknowledgement numbers that are established at the beginning of the handshake. The 2 sets of sequence numbers have nothing to do with each other, and the acknowledgement numbers are acknowledging the sequence numbers from the opposite side. Remember that it's really about here's what I sent, and here's what I got from you, and here's the next thing that I expect, which is just incrementing the data by 1. Thanks for watching. Thanks for listening. Like and subscribe if I helped, and may your packets always reach their destinations, especially if you're using sequence and acknowledgement numbers to make sure they got there.